Hello, dear students. Welcome to the first lecture of Semiconductor Electronics. This is the 14th chapter of class 12 physics. In this lecture, we will be discussing the classification of solids on the basis of their conductivity. Then we will go to energy levels and energy bands, the concepts of energy levels and the energy bands. Mainly, we are discussing the energy bands. Uh, then we will go to the energy band diagrams or energy band diagrams. How can we draw the energy band diagrams in solids? Okay, our first question is give the classification materials on the basis of conductivity. According to the conductivity of materials, they can be classified into metals, semiconductors, and insulators. What are metals? Metals means the materials which have very low resistivity and or high conductivity are called metals. Metals, uh, the main conductors are metals. Copper is a good conductor. Aluminium is a good conductor. The best conductor is silver, Ag. Okay. Uh, and many other materials are conductors. So all these are metal. These are called metals. Metals have free electrons. So they have good conductivity, and the resistivity is much less. You can see the resistivity in ohm meters. It is 10 raised to minus 2 to 10 raised to minus 8. The negative powers, this minus 2 and minus 8, shows that the resistivity is very small. And the conductivity, the conductivity is the reciprocal of resistivity, 1 by rho. Okay, so when you take the when there is when there is in the lower limit, you can see it is 10 raised to minus 2. So when you take 1 by, when you find 10 raised to 1 by 10 raised to minus 2, it is 10 raised to 2. That is the conductivity. And so here it is 10 raised to minus 8, here it is 10 raised to 8. So when you write the conductivity, it is in the range 10 raised to 2, I mean 100 to 10 raised to 8. 10 raised to 8 is 10 crores. The unit SI unit used is Siemens meter inverse. Siemens, that's the reciprocal of this. Here 1 by ohm meter, reciprocal of conductivity 1 by ohm meter, ohm inverse. Ohm inverse is usually represented as Siemens. Yes, okay. And meter inverse is uh, has been written here. Okay, Siemens meter inverse or ohm inverse meter inverse, it says a unit of conductivity. So in the case of metals, the resistivity is from 10 raised to minus 2. Resistivity varies from 10 raised to minus 2 to 10 raised to minus 8 ohm meter. In semiconductors, the resistivity is in this range. Here you can see that the resistivity and the upper range of resistivity increases, and conductivity decreases. Okay, actually, the range is overlapping. You see the semiconductors. There is a wide range of resistivity, 10 raised to minus 5 to 10 raised to 6. Here it is. So the conductivity is 10 raised to 5 to 10 raised to minus 6. These are the values which are given in the NCERT textbook. In insulators, they have high resistivity or low conductivity. The resistivity is 10 raised to 11 to 10 raised to 19. Very high values, very high values, very high values, and the conductivity very small values. So insulators do not conduct electricity. We can say insulators do not conduct electricity. Metals conduct electricity. In semiconductors, we will explain the case of semiconductors in detail in the coming lectures. Here I am going to the concept of energy bands in solids. Concept of energy bands in solids. So when we come to the situation of energy bands in solids, actually we study uh, yeah, uh, in the chapter of atoms. You may have studied the energy levels. You will have studied, if you have already covered that chapter, you you should have studied the energy levels in hydrogen atom. uh, it's according to the Bohr model, the energy levels in hydrogen. So in hydrogen atom, we say energy levels energy levels of hydrogen atom, each atom. So for an individual atom, Or for an isolated atom means atom which is not influenced by its surroundings. Okay, for an isolated atom, there are energy levels. In hydrogen atom, the energy levels is given by the formula En is equal to minus 13.6 electron volt divided by n square. If you have studied the chapter 12, not chapter 13, chapter 12, when you study the Bohr model, you will study the derivation for this, or at least this equation you can study. Uh, the energy levels of hydrogen atom, this is the principal quantum number. Uh, the energy levels of hydrogen atom is given by this formula minus 13.6 eV by n square. So when n equal to 1, when n equal to 1, the energy, when you put n equal to 1, it is the energy is minus 13.6 electron volt. When you put n equal to 2, it is 2 square 4, so minus 13.6 divided by 4 gives some energy which is minus 3 point, I think it is minus 3.4 electron volt for n equal to. And when you substitute n equal to 3, that energy is nearly 1.51 electron volt with a minus sign, n equal to 3. And there are some other energy levels when they go to higher principal quantum numbers. I mean n equal to 4, n equal to 5, etc. They comes close to each other. Yes, here I want to highlight the fact that in hydrogen atom there are energy levels, not energy bands, energy levels. When we come to the molecules, hydrogen molecules, there will be, you will have studied the hybridization in molecules. Okay, uh, there also there are energy levels. Even though there is hybridization, uh, there is a mixing of orbitals. All those things are there, but there will be energy levels. The concept is that of energy levels. Okay, so in individual atoms or isolated atoms, there are energy levels. But when we come to the solids, the concept we consider uh, or we have to consider energy bands when we come to solids. For individual atom, there are energy levels. For gas also, gases, you know, when we take gas in a container, you have studied kinetic theory of gas in class 11, the 13th chapter of class 11. When you take gas in a container, the molecules are very far away, far apart. There is plenty of spaces between the molecules. They are not closely packed, they are usually in random motion, and um, each molecule has some distance from the other molecules. So mm, uh, they are like isolated atoms. There is no influence of other molecules on a particular molecule, so they are like isolated atoms. So they also have energy levels. Gases have energy levels. But when we come to the solids, the situation is different. What is the difference in solids? In solids, atoms are very close to each other. Atoms are very close to each other. I will explain that in another side. Atoms are very close to each other. Let me draw an atom. Suppose this is an atom. This the atoms are arranged like this. Atoms are very close to each other. Okay, that we say it is close packing. We say it is close packing in atoms, in solids. I am representing atoms as big spheres. So let me copy this again. So the atoms are arranged like this. So consider the nucleus of atom. Let me draw a small sphere. Yeah, okay. These are the nuclei. Let this nucleus are very small, and at the center, Okay, these are the nucleus of those atoms. Let me copy it again. Let these blue spheres represent the nuclei of these atoms. So in solids, so we are discussing the case of solids. In gases, we found that there are energy levels, but in solids, instead of energy levels, there are energy bands. Instead of energy levels, there are energy bands. We are coming to that idea. Okay, so uh, according to Niels Bohr and Rutherford, the electrons are revolving around the nucleus. Like suppose consider an electron which is revolving here around this nucleus. It is revolving here around this nucleus, and this nucleus, this electron is revolving in some path. Okay, let me use another color so that you can see it very clearly. So um, this an electron. This electron is attracted by its nucleus. I am saying that the nucleus of the same atom. Okay, but uh, here there is a problem. Since solids are closely packed, in solids, since the atoms are closely packed, this electron will feel attraction from the neighboring nuclei also. The neighboring nuclei also, or the nuclei of neighboring atoms also attract this electron. Okay, this neighboring nuclei also attract this electron. So the energy levels of the electron, I think you know that the energy levels are decided by the force, the electrostatic force acting on the electron. Usually for an isolated atom, if you consider an isolated atom, what is the case? Isolated atom. For an isolated atom, the electron in an isolated atom, suppose this is an isolated atom, the electrons, one electron, this isolated atom is attracted by its own nuclei. Okay, its own nucleus. Okay, so this electron is attracted by its nucleus. So this attraction determines the force, and this force determines the energy levels. Okay, energy levels. But for this electron, the attraction, there is attraction from the nuclei of neighboring atoms also. So in a solid, the energy levels of a of an electron is determined by a group of forces, like it's let this is F1, this is F2, this force is F3, and so on. So the total force is F1 plus F2 plus F3 plus, and some other forces from the neighboring nuclei. So this determines the energy levels. So this energy will not be same as the energy of an individual or isolated atom. So in solids, the energy levels for an individual atom, if the energy level is this particular level, uh, for the for that atom, when it is in a solid or a crystal structure, the energy level will be shifted. The energy level will be shifted. Okay, slightly shifted. The energy level will be different from this. Okay, there will be a shift in the energy level because the energy is determined by the not only the nucleus of the that particular electron, but also by the nuclei of neighboring atoms. So the energy levels of a isolated atom and the energy levels of an atom uh, in a solid are different. One more fact is there, one more thing we have to understand is that if you consider another electron, its its energy level is determined by its surroundings. Its energy levels are determined its surroundings. So the energy level of this electron will not be the same as the energy level of the previous electron. The energy level of this electron can be different, or it will not be same as the energy level of, for this electron. Let me draw the energy level by this red color. So the energy level of this electron can be different from the energy level of the other electron. If you consider another electron, its energy level will be can be different. The energy level of this electron can be slightly different. There is only small difference, but eh, when you consider thousands of electrons in a solid, or lakhs of electrons in a solid, the energy levels will be different. The energy levels can be different. So you have to draw so many energy levels. Let me use the same colors, same color itself. So for a set of electrons in a solid, the energy levels, there will be a large number of energy levels, infinite number of energy levels, which are very close to each other. And we consider this set of energy levels as a band. We call this as a band, energy band. Okay, so in solids, instead of considering individual energy levels, we have to consider energy band. Band means it's a range of energy. Band is a range of energy, range of energy. For example, let this be minus 3 electron volt, and this is minus 5 electron volt. So it's a range of energy from minus 3 to minus 5 electron volt. Okay, or let it be like minus 1 electron volt, minus 3 to minus 1 electron volt. Okay, so it's increasing, energy is increasing. Minus 1 is greater than minus 3. As we go up, energy is increasing. It's a energy band diagram. Okay, so in metals, uh, the energy levels of each electron is different from that of the electron, can be different from that of the other electrons. And so the reason is that the neighborhood of one electron is different from the neighborhood of other electrons. So its energy levels, force are different. So the energy levels are different. So we will get a large number of uh, very close energy levels, which uh, which can be considered as an energy band. Energy band. In solids, mainly there are two bands of energy. Mainly there are two bands of energy. One is the valence band, and the other is the conduction band. I will explain it in the next page. One is the valence band, the other is the conduction band. So, uh, valence band means the energy of the electrons, energy of the valence electrons. Usually, the valence band will be fully occupied, fully occupied. And there is another band which is known as the conduction band. Conduction band. Conduction band means the range of energy possessed by conduction electrons. Conduction band is the range of energy possessed by conduction electrons or free electrons. This is the energy range of free electrons. Energy range of free electrons. This is for the energy range of valence electrons. Valence electrons. Actually, the free electrons are valence electrons. When they get when when are they becoming free? They become free when they get energy from heat or some external energy. When they get some external energy, they will come out of the bonds, then they will be free. Okay, so free electrons means that can move anywhere inside the material. Suppose these are metal sheet, and there are free electrons inside the metal. Let it be copper. Free electrons means they can move anywhere inside the metal. They are not belonging to a particular atom. They can move anywhere inside this metal. Okay, that is free electron. Valence electrons are mainly valence electrons are in the bonding, in the crystal structure. They have particular seats in the crystal structure. Okay, so mainly they are in the bonding. The electrons in the bonds or crystal structure are called the valence electrons, and the free electrons are called conduction electrons. Okay, free electrons. If I give an analogy, suppose the case of um, people traveling in a bus. Um, Suppose there is a great rush in the bus. So all the people, all the travelers, they don't have seats. Okay, some of the travelers have seats. They're sitting in seats in their seats, but some others are standing. So in a bus, there's travelers with who are sitting, as well as some are standing. This free electrons can be compared to those who are standing inside a bus, and the valence electrons can be compared to those who are sitting in seats. Okay, they have seats. They have seats. Okay, so the free electrons are the people who are standing in a bus. Standing people. Okay, they can move anywhere. If there is space, uh, they can move anywhere. But here, these electrons are fixed. They have particular seats. Okay, they are balanced. You can compare with the people who are sitting on their seats. Here, the people are the standing people. Free electrons can be compared to the standing people. Okay, this analogy is very good in understanding the coming concepts. So there are two energy bands in a solid, even it is a metal, semiconductor, or insulator. Or in all those solids, there are two energy bands: the valence band and conduction band. So I'm coming to the those concepts. Now already I have explained. I will read this passage. Define energy bands in solids, or what is the concept of energy bands in solids? In solids, atoms are very close to each other. So the outer orbits of electrons in the neighboring atoms come very close to each other. The outer orbits of electrons of neighboring atoms come very close to each other, or even overlap. Inside a crystal, each electron has a unique position, and no two electrons have exactly the same pattern of surrounding charges. The neighborhood is not same for uh, two electrons. So the energy level of each electron is different, and these energy levels are very close to each other, so that they can be treated as continuous. The range of energy possessed by the electrons in a solid are called energy band. This is the definition of energy band. The range of energy possessed by electrons in a solid are called energy bands. Now, this is the answer of definition of energy bands. Okay, this is taken from the NCERT textbook. Okay, I have made it brief for that you can answer the question like this for board exam. Okay, so you can study, you can take a screenshot of this answers so that you can study. Okay, now there are, as I told you, there are two energy bands. One is the valence band. What is the definition of valence band? It is a range of energy possessed by valence electrons, and it is a most occupied band. Most occupied band. Okay, it is not empty, it is a fully occupied band. Usually it is a fully occupied band. Conduction band is the range of energy possessed by the conduction electrons. It is a least occupied band. What is the concept? The least occupied and most occupied, actually there are uh, other energy bands also in the solids. When you consider the solids, there are other energy bands. What is the concept of other energy bands? Other energy bands means there are energy bands of inner orbits or inner electrons. Actually, what is valence band? It is a range of energy possessed by valence electrons. You know, valence electrons. What is conduction band? Range of energy possessed by conduction electrons. And both valence and conduction electrons belongs to the valence shell. You know, valence shell. But there will be some other energy bands also for the lower orbits, for the electrons in the lower orbit. Okay, okay, lower orbit. Okay, so uh, uh, this is valence band, this is conduction band. Valence band is the energy range of the valence electrons, the energy range of the inner electrons. or inner orbit electrons will be less, if for inner orbits or electrons in the inner orbits, okay, will be less. And the conduction band, uh, the valence electrons which are free from the bonds are conduction electrons. They belongs to the conduction band. This is the most occupied band in a crystal. This is the most occupied band, and this is the least occupied. Sometimes there will be some electrons here, and it can be empty also. Conduction band can be empty also. Okay, so coming to the fact, the the energy difference between the bottom of the conduction band and the top of the valence band is called the forbidden energy gap. What is forbidden energy gap? See this diagram. This gap is known as energy gap, forbidden energy gap. Forbidden means there are no energy levels here. That means no electron can have an energy in between these two levels. Suppose this is a minus 3 electron volt and this is minus 2 electron volt, so there is a gap of 1 electron volt. So no electron can occupy these levels. Otherwise there are no levels, or there are no seats there, so nobody can occupy those energy levels. So it is called forbidden energy gap. So the energy gap between the topmost level of valence band and the bottommost level of conduction band is called the forbidden energy gap. Okay, so you can study these definitions. Now coming to the energy band diagram. How can we draw the energy band diagram in metals, semiconductors, and insulators? Okay, so first of all, in metals, how can we draw the energy bands in metals? In metals, as given in NCERT textbook, there are two cases. There are two cases of energy band diagram. Two energy band diagrams. For some metals, one energy band diagram will suit, and for the other, for some other metals, the other energy band diagram will suit. What I'm saying is that for many metals, the energy band diagram is like this. There is a valence band, which is a fully occupied band, valence band. I'm writing VB, valence band, and the other one is a conduction band. Let me use another color. The other one is the conduction band, and this conduction band is overlapping with the valence band. And what is the advantage of this? So when the valence band and conduction band are overlapping, uh, some of the electrons, this means that some of the electrons have energy to conduct. Conduct means to carry current or to move anywhere in the inside the metal. So in this diagram, actually this is the energy band diagram. So this axis is the energy. As we go up, the energy increases. So some of the valence electrons have energy to be in the conduction band, or to conduct electricity. They have energy. So they're free. Some of the valence electrons are free. You can say they are free. Okay, so this is the case of some metals or many metals. This is the common energy diagram for metals. But in NCERT textbook, one more diagram is given. One more diagram is given in the NCERT textbook. It is like this. There is a valence band. This valence band is not fully occupied. It is partially empty. Partially empty means up to this it is filled, but there are some empty levels also here. Valence band, and there is conduction band, which is partially filled. Conduction band which is partially filled. Somehow there are some electrons in the conduction band. This is the energy band diagram possessed by some other metals, some other metals. So for some metals, this is the energy band diagram. For other metals, okay, there are two groups of metals according to the band diagram. Some other metals possess this second energy graph, energy diagram. And so energy band diagram. Okay, so in this case, what happens is that the valence band, some of the levels in the valence band are unoccupied. There are some empty levels in the valence band. Empty levels means they will help for the conduction. The conduction band, these are the electrons, you know, these are the electrons which are free, electrons which are free. So there are some electrons in the conduction band, means they can conduct, they can move, that will produce a current, that will produce a current due to the flow of electrons. But empty levels in the valence band, imagine the situation like this, in a bus, there are many seats and some of the seats are vacant, some of the seats are vacant. Okay, I will simply represent the, I'm not drawing people, but simply represent points like this. This is this is occupied, 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 and this also is occupied, and some other seats are vacant. So what happens is that this, a man in the seat can go to this seat, since there is vacancy. So what will happen, this electron will come to this, sorry, this electron will come to this position, and this seat is now vacant, the vacancy come to this. Okay, so electron goes to this, means vacancy come here from this seat to seat, this seat was initially vacant, now this seat is vacant. So okay, so the empty levels in valence band can uh, produce a movement of electrons, can produce a movement of electrons. If some of the seats are vacant in a bus, you can move to another seat. Okay, some preferable seat, you can move to some preferable. But if all the seats are filled, you cannot move from one seat to another, because all the seats are occupied. So some empty levels in the valence band, they produce, some empty levels in the valence band, they produce conductivity. Okay, they allows the movement of electrons from one level to another level. Okay, if all the levels are filled, that will not happen, that will not happen. A fully occupied or full valence band, the valence band which is full, uh, cannot produce the movement of electrons. But if some of the seats are vacant, they can produce movement of electrons. Okay, I think you got the point. So this produce uh, the conduction. Okay, and this free electrons also produce the conduction. So this corresponds to the conduction band, the current due to the movement of electrons in the conduction. This current due to the movement of electrons in the valence band. Okay, so these are the two cases in the case of metals. And so how to answer the question? You can write these sentences. These are the diagrams that we have uh, this is the this is for first. I have drawn this as the first, the overlapping case. This is the overlapping case. The valence band and conduction band overlap each other. Overlap. Okay. I drew this as the first case. This was I drew this as the second case. Okay. Overlap each other. So there is no energy gap. The energy gap here. Here there is a small energy gap, but it is very small, very small. And there are some empty levels in the valence band, and some there are some electrons in the conduction band also. Okay, so these are the two cases in metals. In certain metals, I am reading the passage. In certain metals, the conduction band is partially filled and the valence band is partially empty. Okay, this case, then the electrons in the lower levels of the valence band move to its higher levels. There is a there can be a motion in the valence band from the filled levels to unfilled levels, making conduction possible. Okay, uh, here also there can be the electrons in the conduction band also can move. Okay, in some other metals, the valence band and conduction band overlap each other. This is the overlapping case, or the second case, overlap each other. Then the electrons in the valence band can easily move to the conduction band. Okay, so these are the uh, two diagrams for metals. Okay, this is more common in most of the books. Only this diagram is given. In most of the books, this diagram is given. Okay, So you can study in NCERT, both the diagrams are given, and it is said that for some metals this is the case, and for some other metals they also show this type of band diagram. Okay, I think you got the idea. uh, if you want to draw a single diagram, you have to draw this one. This is more important, and or this is, I understand that this is more common in metals. Okay, and only a few metals possess this type of energy band diagram. Okay, so if you want to draw only a single diagram, you can draw this diagram. And coming to the case of semiconductors, in the case of semiconductors, there is a small energy gap between the valence band and conduction band. This gap is very small, it is less than 3 electron volt. If the gap is greater than 3 electron volt, the material is called an insulator. If the gap is greater than 3 electron volt, energy gap is, if the forbidden energy gap is greater than 3 electron volt, it's called an insulator. So uh, I think you got the classification. If the energy gap is less than 3 electron volt, um, the semiconductor, the material is a semiconductor. Okay, in semiconductors, I'm reading the sentence. In semiconductors, there is a small energy gap between the valence band and the conduction band. In insulators, there is a large energy gap greater than 3 electron volt between the valence band and conduction band. These are the case of insulators. This is the case of semiconductors. In semiconductors, there are no electrons in the conduction band, empty. Empty. I am adding one more word, at room temperature. Sorry, at 0 Kelvin. 0 Kelvin means absolute zero. Absolute. What is meant by absolute zero? 0 Kelvin. 0 Kelvin temperature. The lowest temperature that can be reached by a substance. It doesn't mean that substance have reached that temperature. Uh, uh, it is a lowest temperature that substance can occur. Absolute zero. Absolute zero. So absolute zero, the conduction band of semiconductor is empty. When temperature increases to room temperatures, some electrons will be there in the conduction band. That I will explain in the next video. Okay, so in semiconductors, you have to study that when the band diagram, when you study the band, you have to study that in metals, in most of the metals, the valence band and conduction band overlap each other. But in some metals, there is a case that the valence band is partially empty and the conduction band is partially filled. So this partially empty levels in the valence band constitute a conduction, and this electrons in the conduction band can also contribute to the conduction. Okay, in semiconductors, there is a small energy gap between the valence band and conduction band. In insulators, there is a large energy gap between the valence band and conduction band, which is greater than 3 electron volt. In semiconductors, it is less than 3 electron volt. Okay, okay, this is what about the energy diagrams in energy, and the concept of energy band and energy diagrams in solids. Okay, so we studied that in the case of gases. In the case of gases or individual atoms or isolated atoms, what happens? There are energy levels, but in the case of solids, there are energy bands. Which are the two main energy bands in solids? Valence band and conduction band. Okay, now and we studied how to draw the uh, energy bands in different materials, metals, semiconductor, insulation. I think the idea is clear to you. Usually when you think of the valence band and conduction band, you can think like this. These are the energy of valence electrons, or you can see that uh, you can think that the valence band is the energy of some the electrons which are in bonding. Bonding means, in a solid, the each atoms attract each other. Or suppose in a covalent solid, what happens? There is a bonding, covalent bond between the atoms. So the electrons which are shared between the atoms, okay, even in the ionic bond, there is an attraction. There are bonds, ionic bonds. So the electrons which are participating in the bonds, their energy levels comes to this valence band. The free electrons which are not in the bonds, not in bonds means they can move, they have no bonds. Okay, so they can move, they have the energy in the conduction band. Their energy is much slightly greater than that of the valence band. They belongs to the conduction band. So these are the energy levels of electrons in bonds, and these are the energy levels of free electrons. Okay, okay, so I think the idea is clear. We will meet in the next lecture. Thank you.